Okay, we're gonna pick up exactly where we left off in Monday's class. Does anyone need the notes? It's the section 7.5 notes. Okay, we'll finally be finishing up like partial fractions today. There's just maybe 1.5 more examples I want to go through. So this is where we left off on Monday. So we started talking about like what happens when we have some sort of proper rational function we want to integrate using partial fractions. And it was a little bit different from what we saw when we just had linear factors, right? When we just had linear factors, looking at like this previous example, you just have like a over x minus 1, b over x plus 2, and then c over x plus 2 squared. So in the numerator, you just have a constant. But when you have irreducible quadratic expressions in the denominator, inside of the numerator now, you have to have linear functions instead, right? So we looked at one example before going through like this larger integral right here, where if we have 4 minus 12x, and then in the denominator, we have a linear factor, and then this irreducible quadratic factor, x squared plus 4 squared, then we end up getting 1 over x plus 1 over here. But then you also have other fractions of the form of like minus x over x squared plus x plus 4, and then also this minus 4x plus 12 over x squared plus x plus 4 squared. So this is a little bit unusual. Like it's not something that would show up in the linear case, right? Because you have a linear expression in the numerator now. And so let's go through an example. And I also pushed back the due date for the reading assignment. I think it was originally due on Monday, and I pushed it back to tomorrow. It just was like a random day pretty much. On the reading assignment, you have to use the technique that I'm about to show now. And so we have something of the following form, and I wrote this out on Monday, but I'll write it out again now. So the first step is we want to write out the form of the partial fraction decomposition. So I'm just starting off with the original fraction inside of the integral. And so we're going to have, right, we have two terms. We have a linear factor, but then we also have an irreducible quadratic factor in the denominator as well. And so the first term isn't really anything special. We'll just have a term that corresponds to the x plus 3. So we'll have an a over x plus 3. And so what's different now is we have an x squared plus 9 in the denominator. So that's irreducible quadratic. So now we're going to have a bx plus c in the numerator. So the reason why we have a linear function now in the numerator is this is the largest power we can have, so that this still remains a proper rational function, right? Like we can have a degree 1 polynomial because we have a degree 2 polynomial in the denominator. So this is still a proper fraction, so things still work out. And so the first step is pretty much the exact same as the first step in the previous examples we went through, right? So the next thing we'll do is we'll multiply through by x plus 3 over x squared plus 9, or times x squared plus 9. So the next thing I do is like we multiply by x plus 3 and then x squared plus 9. If you do this, you'll end up getting 18 is equal to a. So if you multiply through by x plus 3 times x squared plus 9, this x plus 3 here cancels out with this x plus 3 here. So you'll have an x squared plus 9. And then this is going to be plus bx plus c. And again, if you multiply through by x plus 3 times x squared plus 9, the x squared plus 9 cancels out with this x squared plus 9. And so this will just be multiplied by x plus 3. Okay, and so usually what we were able to do for the linear examples at this point is you could just plug in specific values of x and then determine what the constants are going to be from there. And you can actually do this to solve for a, right? If we plugged in x is equal to minus 3, and now this term would go away, and you'll get a is equal to 18, or a times 18 is equal to 18. So you can determine a is equal to 1 right off the bat if you wanted to. But we're going to do things a different way because it will work for a, but it's not going to work for b and c. So another way of thinking about this is let's just multiply everything through to see what ends up happening. All right, so we'll multiply through and expand on the right-hand side. So we have 18 is going to be equal to ax squared plus 9a. And then we FOIL these two terms out. So we'll have plus bx squared plus 3 times bx plus cx plus 3 times c. And so what we're really doing is we're just setting two polynomials equal to one another, right? I mean, it doesn't look like it on the left-hand side because it's just a number, but a number is still just a polynomial. It's just a polynomial of degree 0. So this is like a degree 0 polynomial, and this is a degree 2 polynomial. So what we can do is we can compare coefficients with like the corresponding degree. So what I mean by this is like, this is really the same thing as like 18 you can think of as being 0 times x squared plus 0 times x plus 18. And then on the right hand side, you can just copy and paste what we had already, right? And so what this tells us is that the components or the coefficients for x squared, right? It should end up being equal to 0, right? You can't have like a non-zero x squared term being equal to something that doesn't have an x squared term, right? So I'm going to write things out. I'm explaining in too much detail, but maybe it's helpful. So I'm going to do it anyways. So this is plus 18. So what I suggest doing is now we can divide, like you can combine like terms with one another, right? You can combine ax squared and bx squared. So we really have like a plus b times x squared. And then you can combine the like terms for the c terms as well. So we have a 3bx and then a cx as well. So we have a 3b plus c times x. And then lastly, we have the constant terms. So the constant terms are just going to be 9 times a plus 3c. And so what I was saying is, right, like the a plus b has to be equal to 0, right? Like if this were non-zero, then you'll have an x squared term here, but then you don't have an x squared term here. So it wouldn't really make any sense. So we need to make sure that these two coefficients are equal. So a plus b has to be equal to 0. 3b plus c has to be equal to 0. And then we have to have that 9a plus 3c has to be equal to 18. And that will allow us to find a way to find a, b, and c now, right? So we have to have that 0 is equal to a plus b. We have to have that 0 is equal to 3b plus c. And then we also have that 18 is equal to 9a plus 3c. All right, so this is like the degree 0, or this is degree 2. This is degree 1. And then this is degree 0, or like the constant term. Does this make sense so far? Any questions about how I got these equations? Okay, and so now it's just a matter of solving this system of linear equations. And it's also like, we kind of determined that a was equal to 1 in the beginning, so then that'll tell you b is equal to -1. But we're doing things the hard way on purpose. Okay, so this is, so if we have a plus b is equal to 0, this is going to tell you that a is equal to minus b. If we have 0 is equal to 3b plus c, this tells you that c is equal to minus 3b. And then for the final line, we have 9a plus 3c is equal to 18. But we know how to write a and c in terms of b, right? So now we can substitute in for a and for c entirely in terms of b, and then we can solve for b. And then once we know what b is, we know what a is, and we'll know what c is as well. So 9a plus 3c is really the same thing as having 9 times minus b, due to the fact that a is equal to minus b. And then this will be plus 3 times minus 3b. And so this is really telling us that we have that 18 is equal to minus 18 times b. And then if you divide both sides by 18 or minus 18, you'll get b is equal to -1. So this tells us b is equal to -1. If b is equal to -1, this is going to imply that c is going to be equal to 3. So this is minus 3 times minus 1 is equal to 3. And then if b is equal to minus 1, it tells us that a has to be equal to 1. So this is really equal to minus 1, which is equal to 1. And so now we know what a, b, and c are going to end up being equal to. Okay, any questions so far about how I found a, b, and c? Okay, and then that's kind of that's the new part, right? Everything else is pretty much the exact same as what we did for the linear cases as well. So what we ended up finding is that this integral of 18 over x plus 3 times x squared plus 9 dx, we can really write this as being equal to the integral. So we had a over x plus 3. We have a is equal to 1. So this is just going to be the integral of 1 over x plus 3 dx. And then we found that b was equal to 3, or b was equal to minus 1, and then c was equal to 3. So this is really going to be plus the integral of minus x plus 3 over x squared plus 9. And so you kind of, actually this next integral, you have to be a little bit clever in terms of how to solve it. So like this first integral, it's pretty easy to solve. Like it's just the natural log of x plus 3. So this is going to be equal to the natural log of x plus 3. This other one, you can't really use u substitution. Like if you use u substitution, you'll have like a 2x that will show up as your d, or like 2x dx. But you have a minus x plus 3 in the numerator. That's kind of hard to deal with. So what I would recommend here is I would split up this integral into two smaller integrals. So this is really going to be plus the integral of minus x over x squared plus 9 dx. And then this is going to be plus the integral of 3 over x squared plus 9 dx. Okay, and then from here, there's still a little bit more work to be done, right? If we wanted to find this integral, we can now use u substitution with u being equal to x squared plus 9. So we'll let u be equal to x squared plus 9. So then du is equal to 2x dx. This will then imply that we have 1/2 of du is equal to x dx. And so what you end up getting for this integral, if you go through with the u substitution, I'm not going to write it out in complete detail. So we have the natural log of x plus 3. This next integral will end up being minus 1/2 times the natural log of x squared plus 9. Again, just by doing u substitution. Like after you do u substitution, you'll have like a minus 1/2 here. This becomes your 1/2 du, and then you have a 1 over u. So you just get natural log of x squared plus 9. And then this other one is actually like one of those arctangent integrals from the beginning of the semester, right? You have something that kind of looks like 1 over x squared plus 1. So you have to rewrite this. So this is really plus 3 times the integral. So you can write it as being like 1 over 9 times x over 3 squared plus 1, like this. Right, this is like stuff we did in the beginning of the semester. I probably won't ask you something like this on the exam, but it shows up every now and then. So if you solve this integral, it'd be minus like all this other stuff. Oh, I forgot the natural log. Hold on. I said it, but I didn't write it. So this is natural log, and then this is natural log of x squared plus 9. And so this will be plus 3. Well, actually, the 3 ends up going away. And you should end up getting this will be arctangent of x over 3 plus c. I think you end up getting a 1 over 3 here, but when you do the u substitution, you'll have another 3 that cancels out with the 1 over 3 you have. So you end up getting something along this line, something like this. So this is why like the partial fraction problems, like they can get really nasty. Like even after you solve all like A, B, C's, and sometimes you'll have like D's and E's as well. Like sometimes the integral after requires a bit more work as well than what you get in the linear case. So, yeah, so this is the final answer for this one. Okay, any questions about this? Yeah, go ahead.
How do we get that second negative x plus 3 over x?
Oh, yeah, I kind of skipped an algebraic step. So like the first thing I did, so I'm like starting from this integral here, this is equal. So I'll just write out, this is like the natural log of x. Actually, we'll just keep it at the exact same, except the one thing I'm changing. So this is 1 over x plus 3 dx. This second integral is really just the same thing as minus x over x squared plus 9 plus 3 over x squared plus 9 dx. Right, I'm just splitting up this fraction into a sum of these two smaller fractions, and then you can distribute the integral to like both terms. Like the integral is linear, so it distributes over sums. So like the integral of this entire thing is really the integral of this thing plus the integral of this thing. So I was just using this fact. So if you do like the integral of f of x plus g of x dx, it's really the same thing as doing the integral of f of x dx plus the integral of g of x dx. Where f of x in this case is this thing, and then g of x is this guy. Does that make sense? Mm-hmm. Yeah, so I skipped this step in like writing it. Okay, any other questions about this example? Okay, yeah, I kind of want to be done with partial fractions. There's one other example. This was actually kind of like on the group work yesterday, except I split it up into 3 smaller problems. I'm not gonna, it would take the rest of the class to go through this one. Like this one's pretty brutal. It'd be the worst example of the entire class. But it's like kind of the same idea. I wouldn't ask something like this on the exam. But you end up having like an irreducible quadratic factor that's to the second power. So you're going to have 5 constants to solve for. And then eventually you find the integral, or you set up the integrals, and then you have to do like trig substitution. And then in the trig substitution, you have to use like the reduction formula. So it gets pretty nasty. So I'm not gonna focus on that one. And then these other examples are kind of easier than the ones we've been doing. You can do these for practice, but I think it's time to move on to the next section. Okay, any final questions about partial fractions before we move on to the next section? Okay, so this next section, it's not as bad as improper fractions or as partial fractions, but it still is like a section people have some difficulty with, I think, just because it brings back limits and it's kind of lots of confusing. Did everyone get the notes? Okay, so next we're going to be going over improper integrals. And so usually these problems aren't too terrible. But again, it's like bringing back limits, and you're incorporating like limits and integrals. So it can get a little bit dicey in some spots. There's like a little bit more algebra you have to do than in the previous sections. And so the idea with improper integrals is, so far when we've been asking about finding the area under the curve, we've only been looking over a finite domain. So we can always assume that we have, well, maybe not always assume we have a finite area, but we've always been looking at like finite integrals, right? We haven't been looking at like infinite integrals or infinite area. And so like a natural question to ask would be like, what if we wanted to find the area underneath a curve of the following nature? And so what makes this curve more exceptional, or like the area under this curve more exceptional, is the fact that the x, like the domain we're integrating over, is unbounded, right? So the smallest, we're going to minus infinity in this direction, and then we're going to plus infinity in this direction. So if we wanted to find the area under the curve, we would have to evaluate the following integral. And so this section is concerned with like, how would we compute this integral, where the bounds of integration go from minus infinity to infinity, or if we have just like infinity and this is a constant, or this is minus infinity and this is a constant. And so the natural way of thinking about it is like, we'll just look at the limit, right? We'll look at the limit as some number goes to infinity here, and the limit as some number goes to infinity here. And so when we have an integral of this form, it's what's called an improper integral. And there'll be other forms of improper integrals we'll look at over today and Friday as well. And so for this example, even though the domain of integration ends up being infinite, the total area itself ends up being finite. So just because you have an improper integral doesn't mean that you're going to have an infinite area. Otherwise, it'd be kind of boring. You just have to determine if it's like plus or minus infinity, right? So you can have infinite, like an infinite domain, but still have finite area. And so there are two main ways an integral can be improper. The first is the one that we looked at already. So we can have that the interval of integration is going to be infinite. But the other example is you can have a finite interval of integration, but the integrand, i.e. the function you're integrating, can tend to infinity on a finite interval. So you might have like a vertical asymptote, right? If you're doing like the integral of 1 over x and part of your domain included x is equal to 0, then you would expect there to be some issues, right? Because you have a vertical asymptote at x is equal to 0. And so I'll talk more about that later on. But first, we're just going to deal with improper integrals over infinite intervals. And so this takes the following three forms. So this is what I said before, but this is in writing. So these are the three kinds of improper integrals we can have. So it's like minus infinity to a, so that's infinite. 0 or a to infinity is an infinite interval, and then minus infinity to infinity, of course, is an infinite interval as well. And so a question could be like, how can an unbounded region end up having finite area? And so we'll just look at a simple example. And so what do we mean by area of an unbounded region? So we'll look at like f of x is equal to e to the minus x. So that's graphed at the bottom of this page. So this is the graph of y is equal to e to the minus x. And so this is the integral, like this shaded region is the integral from 0 to r of e to the minus x. And so the idea is like you start off with computing this integral from 0 to r, which is done here. And then you'll get a finite number because this is a finite interval and we don't have a vertical asymptote anywhere. So if you compute this integral, again, like the integral would just be minus e to the minus x evaluated from 0 to r. And so you end up getting 1 minus e to the minus r right here. But then as r goes to infinity, what's important is if you look at this function as r goes to infinity, this is really just the same thing as having 1 minus 1 over e to the r. So as r goes to infinity, this term here is just going to go to 0. And so you're just going to be left with 1. So that's what's going on in this second equation I have written out. So if we want to determine this integral from 0 to infinity of e to the minus x, all we do is we just take the limit as r goes to infinity, where r is the upper limit of integration that we have here. And so now if you ignore the limit, we just have a finite integral, right? Like nothing's different about what we've done in the past. We just have this finite integral that we compute, and we get this like 1 minus e to the minus r, just like we had before. And then at this point, all you have to do is just apply the limit. So if you apply the limit, you end up getting just this 1 right here. So all you do is just evaluate this integral, and then you just take the limit as r goes to infinity. That's all that's really going on to evaluate this infinite integral. And so then that's what's going on graphically here. So we start off with a smaller r is increasing, and then this is what happens when r goes to infinity. So we have like this horizontal asymptote at y is equal to 0. And so as time goes on, it's like really incremental change that's being attributed to the area. So that's conceptually what's going on. So the formal definition for the improper integral is outlined here. And so for computations, this is really what you're going to be looking at. So for an improper integral, we fix a number a, and we assume that f is integral over some finite interval from a to b, where b is greater than a. So the improper integral of f over this interval from a to infinity is defined as the following limit. So if you want to do the integral from a to infinity of f of x, is this a matter of computing this integral from a to r of f of x dx? and then letting r go to infinity. And then similarly, we have the minus infinity as well. So if we define the following integral and just let r go to minus infinity, you end up getting this integral, or you compute this integral. Okay, so it's like this is one of those sections where you just need to work through examples. Like it's important to have like the what's going on conceptually down, but on the exam, I'm just going to ask you to compute examples, right? I'm not going to focus on like the conceptual side all too much. So for this first example, it wants you to compute the integral from 2 to infinity of 1 over x cubed. Oh, and then I guess, did I say, I don't even know if I said converges. I was like distracted by other things. So what it means for this to converge is it like you need to show that this has like a finite value, right? So converges just means that the limit ends up existing, and then diverges means that the limit doesn't exist. So you have like an infinite limit. So for this one, this first example, if we want to compute this integral from 2 to infinity of, instead of writing 1 over x cubed, I'm just going to write it as x to the minus 3 dx. And so really what we want to compute is we're just computing the limit. So I'm just taking after what I have written up here, right? So I'm going to let the limit as r goes, I'm going to choose some number r, or just denote this number r. So we're going to take a limit as r goes to infinity of the interval or integral from 2 to r. And then we're just integrating x to the minus 3 dx. Right, so all I'm doing is just following what's written up here inside of the box. And so now you pretty much just ignore the limit until the very end. You just compute this definite integral in terms of r, and then you just compute a limit at the end. Right, so this is going to be equal to the limit as r goes to infinity. The antiderivative of x to the minus 3 is just going to be minus 1/2 times x to the minus 2, just by the power rule. So this is going to be minus 1/2 times x to the minus 2. And then we're integrating from 2 to r. And so this is the same thing as the following. So this is going to be equal to the limit as r goes to infinity of, so unlike the previous examples in this class, you actually have to like write out like what happens when you plug in r. Like you can't leave your answer like this. You have to go further and show whether or not it converges or diverges. So I'll plug in like what happens when you get like x is equal to r, and then subtract from that what you get when you plug in x is equal to 2. I'm going to pull out the minus 1/2. So this is really going to be minus 1/2 times r to the minus 2. And then this will be minus 2 to the minus 2. And so you can really write this as being equal to the limit as r goes to infinity. I'm going to move the minus 1/2 in front. So this is really minus 1/2 times this limit. Again, you can like bring constants like outside of the limit because it doesn't depend on r at all. So this is really like the limit as r goes to infinity of 1 over r squared. And then this is minus 1 over 4. And so now it's just a matter of computing this limit, right? And so the limit as r goes to infinity of 1 over r squared is just equal to 0, right? And this gets arbitrarily large in the denominator. And so you end up just getting minus 1/2. So like this, we have this minus 1/2 term multiplied by 0 minus 1 over 4. So you really just have minus 1/2 times minus 1 over 4, which just gives you 1 over 8. So that's all that's going on here. So really like, you're just doing standard integrals, just ignoring the limit, and then you just compute a limit as r goes to infinity or minus infinity at the end. At least for these simpler examples. There'll be more complicated examples later on. Any questions about this first example? Yeah, question.
So at what point, like on an exam, would we stop? So
At 1 over 8.
so we'd have to find like a depth, like an actual one.
Yeah. Yeah, question. Oh, yeah, so we did the limit as r goes to infinity of 1 over r squared. So if you do like the limit of 1 over r squared, or 1 over r cubed, like what's going on is like you're doing like, this is a constant number, so the numerator stays the same, but the denominator gets arbitrarily large. So it's like, this would be like 1 over 1,000, 1 over 10,000, 1 over a million, 1 over like a billion, like as large a number as it gets. So as r goes to infinity, like this denominator, or like this will go to 0, right? Because like this stays the same, but the denominator gets arbitrarily large. Okay. Or you can just see, like if you were to graph this, it would be something like this, right? And so you can see, like as x increases, we get closer and closer to the y-axis, so it becomes 0. Okay, any other questions? Okay, so we'll just compute some more examples. This next example, so I think like the hard part of these problems really isn't like the integral usually, or setting things up, but you have to kind of you have to know what's going on with like stuff like the natural log and exponential functions, and like what it means for a function to diverge or converge. That's kind of the hard part, I would say, for this. So for this next example, it plays out in a similar way. It's really similar to what we already did, actually. The previous example, we did 1 over x cubed, whereas this one, we have 1 over x. So what's different is going to be the power that we have in the denominator. But it turns out it's going to have a huge difference, even though they look similar to one another. So we're looking at the integral from 1,000 to infinity of 1 over x dx. And so this is the same thing as just doing the limit as r goes to infinity of this integral from 1,000 to r of 1 over x dx. Again, all I did was just get rid of the infinity inside of the limit of integration and just transform it into a limit. So now we have an integral over a finite region, or a finite domain. And so this is really going to be equal to the limit as r goes to infinity of the natural log of x, right? We know the integral of 1 over x is the natural log of x. So this is the limit as r goes to infinity of the natural log of x, evaluated from 1,000 to r. And so now you just plug in these numbers again. So I'd say like the hard part of the problem is really this next bit right here. Maybe it's not hard, but you kind of have to know things about natural log, which people don't like the natural log. So this is really like the limit as r goes to infinity of the natural log of r minus the natural log of 1,000. And so you could note, I mean, you should see from this that this is going to end up diverging from the fact that as r goes to infinity, the natural log of r goes to infinity as well. And then this is just a constant term. You can also write things out in the following way. So you can combine it into a single natural log. This is really the same thing as the limit as r goes to infinity of the natural log of r over 1,000. This is like a useful property. I've written it out before. You've probably seen it in high school and then Calc 1. But this is like a really important property that will show up in the section a couple of times. So if you have like the natural log of u minus the natural log of v, it's the same thing as doing the natural log of u minus, or natural log of u over v. That's what I'm employing to go from this step to this step right here. And so we're letting r go to infinity inside of the natural log. And so like the natural log looks like this if you were to graph it out. Something like this. Not perfect, but that's what it is. So this is like y is equal to the natural log of x. So as x goes to infinity, so too does y, like the corresponding y value. So this ends up being equal to infinity. And like the reasoning being, I'll put it into words because the natural log of x goes to infinity as x goes to infinity. So in this case, we're looking at r, but it's like this is like the concept as to why this becomes infinity. So you kind of have to know this stuff for this section, which I think gives people difficulty. And so because this goes to infinity, just to acquaint you with the terminology. So because this goes to infinity, this means that the integral diverges. If it were a finite number, like we saw here, which I didn't use the term, but this means that it converges. So finite number means the integral converges. Infinite number means that the integral diverges, just to acquaint you with the terminology. Okay, any questions about this example? Okay, and so we kind of showed something, but we didn't really prove it in generality. But you can kind of observe there's a kind of like a trend going on between these two examples that we looked at. So what we saw is when we had a power of x in the denominator that was greater than 1, we ended up getting an integral that converged. But when we ended up finding, when we computed an integral where the power of x was less than or equal to 1, i.e. in this case it was equal to 1, we ended up getting something that diverged, right? And so that's generalized by the following theorem. This isn't really going to show up, but I thought I may as well write it down. There's something analogous for infinite series that will show up later on that kind of is equivalent to this statement. We'll pay more attention to that. But just to get like your intuition going, I guess. So the larger value of p you have in this term here, if like p is greater than 1, then this integral is always going to converge, and it's always going to converge to the following value. But if p is equal to 1 or less than 1, then you always have that it's going to diverge. So you could remember this, but you can always just integrate. Like usually these are the simplest examples, so they aren't really that much work to compute in the first place. Okay, so the next example we'll look at is what's called Gabriel's horn. So this is like kind of an interesting surface, or it has like an interesting property to it. And it's something we'll look at later on as well in chapter 8. So Gabriel's horn is a surface that we obtain by rotating the graph of f of x is equal to 1 over x for x greater than 1 about the x-axis. And so what makes this surface interesting is that it has a finite volume, but it ends up having an infinite surface area. And so what it wants you to do for this example is it wants you to compute the volume contained within Gabriel's horn. And so this goes back, so it's already been like a couple of weeks. I don't know if people remember, but like what we're doing is we're taking a curve like y is equal to 1 over x, which is really this curve right here. And then we're rotating it about the x-axis, right? So we have like a volume of rotation or volume of revolution, which was on the first exam, right? And so if we're taking f of x is equal to 1 over x and we're rotating about the x-axis, does anyone remember like how you would find the volume? Like do we do like the shell or do we do like the disk, or what method do we use? Yeah, it'll be the disk. Yeah, so we use the shell usually when we have like vertical axes, and then we use the disk when we're doing the horizontal axes. And so we're rotating. Maybe I don't have to put this in the words, but I'm going to anyway. So we're rotating y is equal to 1 over x about the x-axis. And so this means we're going to be using the disk method to find volume, right? It ultimately wants us to compute the volume. So we're going to be using some old equations. And so what this is going to tell us is we have that the volume, let's use a different color. We have the volume. For using the disk method, you should be thinking in terms of like the area of a circle. So it's going to be pi times this integral. I'll write out the bounds of integration later on. We're taking 1 over x, right? So if we have like an arbitrary cross section, this is like x, the height is going to be 1 over x. And so if we have this circle, this is a circle of radius 1 over x. All right, I'm just like reviewing what we've done a couple of weeks ago. So this will be 1 over x squared, and then this will be dx. And so it tells us in the beginning that we're considering values of x that are greater than 1. So we're going to be integrating from 1 to infinity. And so this is where the improper integral comes into play, right? We're computing the volume of this surface of revolution, and we don't have a bound on what our x is going to be. So we're going from 1 to infinity. But now we know that we can just take this and then we can write it as a limit. And we also know from the previous page that we're looking at 1 over x squared, right? If you distribute the square, you just get 1 over x squared. we have x, or we have 2 is greater than 1. So we already know this is going to end up converging, and it'll converge to the following value. We're gonna go through the computation nonetheless. So we're going to rewrite this as being equal to pi times the limit as r goes to infinity of 1 to the r, or 1 to r. And I'm going to write 1 over x squared as just x to the minus 2 dx. And so this is a straightforward integral to compute. You just use the power rule for integration. So you add 1 to minus 2, so you'll have x over minus 1, and then it'll be to the minus 1 power. So this will be equal to pi times the limit as r goes to infinity. And then we'll have a minus 1 over x. And this will be evaluated from 1 to r. And so this is really the same thing. You can pull out the minus 1 and bring it out in front. So this is going to be minus pi times the limit as r goes to infinity of 1 over r minus 1. Right, so just plugging in. So I pulled out the minus sign, brought it in front. Then I'm just plugging in x is equal to r to get 1 over r, and then plugging in x is equal to 1 to get this minus 1. And so now it's just a matter of computing this limit as r goes to infinity. As r goes to infinity, 1 over r is going to go to 0. Again, like the denominator is getting arbitrarily large. So this becomes closer and closer to 0. And so you're just going to have minus pi times minus 1, which is going to be equal to pi. And so this is how you would find the volume of this surface of, or region of, whatever you call it, volume of rotation, right? Where like x is greater than 1. So hopefully it's not too scary so far, hopefully. Like a lot of these integrals, like I'm not going to give you like really difficult integrals for this section. But you'll see later on some of like sometimes like this part can get really messy, like computing the limit. Can get pretty messy. Like we'll see examples where I have to use like L'Hopital's rule and stuff like that. But so far we're starting off like pretty gently. Okay, any questions about this example before we move on? Okay, so we'll go through one more example and then we'll call it a day, or maybe half of an example. And so far we've only been looking at integrals where we have one limit of integration that goes to infinity instead of like both of them. So you can have like, what if we have like a minus infinity here and an infinity here? And so that's what the next example we'll look at is going to cover. So we have like a doubly infinite improper integral is defined as the sum. So if we have this like integral that's going from minus infinity to infinity, what you can do is you can just split it into 2 other integrals, right? You can rewrite this as being the sum of the integral from minus infinity to 0 of f of x dx plus 0 to infinity of f of x dx. I'm just using the following property. So if you have like, I'm not going to write it out. I just realized I have to write out a bunch of constants and inequalities and stuff like that. But you can split up the integrals in the following way, as long as these terms match, right? Okay, and so you can split it up in the following way, and the 0 is arbitrary. If you wanted to, you can make this equal to like 1,000 or like 10,000, but 0 is usually just an easy number to like work with. So like plugging in 0 usually works out pretty well. So we're splitting at 0. But it's really going to depend on what function you have given. So we'll do one last example. It wants us to determine whether or not this integral from minus infinity to infinity of 1 plus x squared dx ends up converging. And then if so, it wants you to find the value that it converges to. And so to begin, we're just going to take this initial integral from minus infinity to infinity of 1 over 1 plus x squared dx. And we're going to do exactly as they're doing here. We're going to make it so we have like 2 integrals. So we're going to write this as being the integral from minus infinity to 0 of 1 over 1 plus x squared dx. And then this will be plus the integral from 0 to infinity of 1 over 1 plus x squared dx. And so we'll just take them one at a time. So we'll look at this one first, and then we'll compute the second one later on. And so if we're looking at this integral, so we're going from the integral from minus infinity to 0 of 1 over 1 plus x squared dx. You can write this as being equal to the limit as r goes to minus infinity. And then we're going from r to 0 of 1 over 1 plus x squared dx. And so this integral here is given by inverse tangent. It's one that we're familiar with already. So this is going to be equal to the limit as r goes to minus infinity of inverse tangent of x. And this is going from r to 0. And so before continuing, let's remind ourselves what the graph of inverse tangent looks like. It looks something like this. So it has vertical or horizontal asymptotes of pi over 2 and then minus pi over 2. Like this. And then the graph itself looks something along these lines. So this is inverse tangent. I'm rushing a little bit because we're running out of time. And so all we have to do to understand this limit is you just have to look at this graph and see what's going on. All right, so this limit is really equal to the limit as r goes to minus infinity of inverse tangent of 0 minus inverse tangent of r as r goes to infinity. Inverse tangent of 0 is just equal to 0. Like you should think like, what do you have to input in the tangent to get 0? And the answer is just 0. So this is going to be the limit as r goes to minus infinity of 0 minus inverse tangent of r as r goes to infinity or minus infinity. And we see that when r or when x, sorry, I'm like, yeah, I wrote this in terms of x. So as x goes to minus infinity, we see that inverse tangent goes to minus pi over 2. So this limit as r goes to minus infinity of inverse tangent is going to go to minus pi over 2. So this is going to be equal to minus, we really have like minus pi over 2, which is equal to pi over 2. So that's the first half. The other half plays out in the exact same way, right? So if we wanted to find, I'll just do this really quickly. And so the other integral ends up being pretty much the exact same. So if we wanted to find this integral right here, it would just be the integral from 0 to infinity of 1 over 1 plus x squared. I'll just tell you, like, you follow the exact same steps over again, except all you change is r is equal to infinity instead of minus infinity. It will change the order of this as well. And if r is going to infinity, inverse tangent goes to pi over 2. So this ends up being equal to pi over 2 as well. This is something you can check on your own. It's pretty much the exact same as what we did before. And so what this implies, to finish up, is that this integral from minus infinity to infinity of 1 over 1 plus x squared dx, this is really equal to pi over 2 plus pi over 2, which is equal to pi. Right, just taking the sum of these two definite integrals that we ended up showing was equal to pi over 2. And so this would be your final answer. I might review it a little bit in next class because I rushed over it, but any questions before I finish class today? Okay, we'll talk more about improper integrals on Friday as well. Oh, thanks.